In this video, we'll look at question 19 from the 2016 paper. So here they start off by saying that the universe is expanding, and that what used to be gamma rays in the early universe now appear as microwaves to us, due to this expansion. And we are supposed to say what happened to the wavelength and frequency of this light during that expansion. Which is a very easy question if you happen to remember the typical frequencies and wavelengths of gamma rays and microwaves. Then you just compare the two and you're done. But let's have a look at how we can try and solve this a bit more systematically. As far as we know, the universe started with a big bang, followed by a period of very rapid inflation in just a matter of a fraction of a second. The radius, our best estimate is that the radius increased about 10 to 78 times. At about 10 to negative 30 seconds, I think. And ever since, the universe has been expanding, except at a much slower rate. And according to a very recent discovery, this rate at which the universe is now expanding is actually increasing. So we talk about the accelerating expansion of the universe. More importantly for us, however, if we have a gamma ray in the early universe, as the universe itself stretches, the space stretches, that wave will have to stretch too, and that means larger wavelength. So lambda increases, and because of this formula, which tells us that the wavelength is inversely proportional to frequency, it must also be that the frequency decreases. Another way of thinking about it would be to say that as the universe is expanding, it's also cooling down. So the energy density decreases. The energy of the individual waves will decrease. And since the energy is proportional to frequency of that wave, it must be that the frequency decreases, and then we can go the other way around and say that the wavelength must increase. This combination, lambda increasing and f decreasing, was option B in the exam. But I also want to show you how this discovery was made, because it's one of the most influential plots in the history of science, this graph in the lower left corner. Up to that point, in 1929, the general sentiment was that the universe is probably static. Not all people agreed with that, but Albert Einstein did. And that's why he introduced something called the cosmological constant into his equations. But Edwin Hubble's discovery in 1929 made him change his mind. And he supposedly said that the cosmological constant was the biggest mistake of his scientific career. Hubble measured the velocity of 22 galaxies, depending on how far they are from us. And he found that almost all galaxies are receding. And the further they are from us, the faster they are going away from us. So the velocity is approximately proportional to the distance. So unless the Earth is in a very special place in the universe, all objects are traveling apart from one another. And that's what we started calling expansion of the universe. I'm not an experimental physicist, but I have always found that Hubble was very bold in drawing this line of proportionality over his scatterplot. The points are clustered around that line, but saying that there is a clear proportionality was a very daring statement, especially at the time when Albert Einstein thought that the universe was static. So who won in the long run? Is it Hubble or Einstein? Well, let's call it a draw, because while Hubble was right about the expansion of the universe, physicists today are trying to revive the concept of cosmological constant, so maybe Einstein wasn't wrong after all.